The universe today is ablaze. Across the vastness, countless galaxies shimmer, each a cathedral of light built from billions of stars. Blue giants burn furiously, white suns blaze steadily, and faint red dwarfs glow with quiet persistence. For now, the cosmos is alive with fire, its nights lit by the fusion of hydrogen into helium, the eternal script of starlight. But physics whispers another truth, that this brilliance is temporary. Every star is a clock, and every clock is ticking. The giants will go first, exploding into supernova, leaving behind neutron stars and black holes. The smaller suns will endure longer, but even they will fade. And when the final red dwarf burns, its last hydrogen atom, the curtain will fall. There will be no encore. The sky will go dark. The universe will enter a silence so deep that no star, no galaxy will ever pierce it again. The image is haunting, the cosmos as a great play, its stars as actors, their roles brief against the scale of eternity. The performance has dazzled for billions of years, but the script already carries its final act, a long night after the last star. And yet, questions linger in the darkness. What becomes of a universe without stars? Does the silence mark true death? Or could hidden processes, unknown physics, or strange quantum whispers ignite a new kind of dawn? To follow the long night is to confront not only the fate of stars, but the fate of existence itself. For most of human history, the stars were believed to be eternal. They hung in the sky as constant lights, unchanging, untouchable, guardians of permanence in a world of fleeting seasons and mortal lives. To the ancients, the stars were not only fire in the heavens, they were symbols of eternity itself. But as science advanced, the illusion of immortality dissolved. The stars were not endless. They were living entities, with beginnings and ends, fueled by delicate processes that could falter, fail, and fade. To discover this truth was to learn that the universe itself carries within it an expiration date. The journey toward the long night begins with the discovery that even the brightest fires must die. The eternal fires questioned in antiquity, philosophers debated the nature of starlight. Aristotle imagined stars as perfect and unchanging spheres of ether. For centuries, their constancy seemed to affirm this. Unlike planets, which wandered across the sky, the stars held steady. They gave no sign of exhaustion or birth, but telescopes began to change perception. In 1572, Tycho Brahe observed a new star, a supernova, though he did not know it at the time. Blazing suddenly in the constellation Cassiopeia, its appearance shattered the idea of an immutable heaven. Stars, it seemed, could be born in brilliance and vanish again. The 19th century, the science of starlight. The 19th century brought the first scientific glimpses into stellar engines. Joseph Fraunhofer's invention of the spectroscope revealed the composition of stars. Their light bore dark lines, fingerprints of chemical elements. Stars were not eternal fires, but physical objects burning matter. The great mystery was there. Fuel. Some thought stars burned like coal or chemical flames. But the numbers failed. No chemical process could power a star for more than a few thousand years. Yet Earth itself was millions of years old, and the stars had burned since its beginning. The riddle of starlight awaited the physics of the 20th century. Fusion, the engine of the stars, the breakthrough came with nuclear physics. In the 1920s and 1930s, scientists like Arthur Eddington and Hans Bethe uncovered the secret: nuclear fusion. In the heart of stars, hydrogen atoms fuse into helium, releasing energy according to Einstein's equation, E equals mc squared. This process could sustain a star for billions or trillions of years, depending on its mass. Fusion explained both the sun's steady light and the varied lifespans of stars across the cosmos. At last, humanity understood. Stars are not eternal. They are nuclear furnaces, consuming fuel. And like all furnaces, they must eventually go out. Mapping the life cycles by the mid-20th century, astrophysicists had charted the life cycles of stars with precision. Massive stars burn quickly, living only millions of years before exploding as supernova, leaving behind neutron stars or black holes. Sun-like stars expand into red giants, shed their outer layers, and cool into white dwarfs, small red dwarfs. The most common stars in the universe burn slowly for trillions of years before fading. The stars that once seemed eternal were now revealed as fragile, finite. Their deaths were not anomalies but inevitabilities. The discovery of remnants with powerful telescopes. Astronomers began to observe these remnants directly. White dwarfs, faint, cooling embers of once bright stars. Neutron stars, ultra-dense. Spheres spinning with ferocious speed, emitting pulses of radiation. Black holes, regions where gravity becomes absolute, swallowing light itself. Each was evidence that the cosmos was not only alive with starlight, but haunted by stellar corpses. The sky was not eternal brilliance, but a battlefield of births and deaths. The finite cosmos. These discoveries reshaped cosmology. If stars are born and die, then the universe itself is evolving. It has not always been as it is now, and it will not always remain. Galaxies, once thought static, are sites of constant renewal. They're gas-forming stars that one day burn out, but gas is not infinite. With each generation of stars, more fuel is locked into remnants, white dwarfs, neutron stars, black holes. Star formation will one day cease. The universe will not sparkle forever. The timeline of Era's astrophysicists constructed a cosmic timeline, a map of the far future, the stellar era, the present age, filled with stars blazing through fusion, lasting for about 10 trillion years. The Degenerate Era, when star formation ends, and only remnants remain. White dwarfs, neutron stars, black dwarfs, and black holes. The Black Hole Era, when black holes dominate, swallowing matter until they too evaporate. The Dark Era, the ultimate silence, when only radiation, dust, and faint particles persist. This framework transformed the fate of the cosmos into something calculable. The universe is not eternal brilliance. It is a sequence of eras, each more silent than the last. The central question emerges. The realization was staggering. Stars are finite. Their lifespans can be measured. The universe itself is moving through stages, from fire to darkness. And so the central question emerged. What happens after the last star dies? This was not a poetic metaphor. It was a scientific certainty. Fusion will end. Light will fade. A long night will follow. But what lies within that night? Heat, death, transformation, or something stranger, remains one of the deepest mysteries of cosmology. For countless generations, the stars had been humanity's symbols of permanence. Empires rose and fell, oceans shifted, civilizations vanished, but the stars endured. To discover that they were mortal was not merely a scientific revelation. It was an existential shock. The heavens, once eternal, were now fragile. And if even the stars would perish, what future could remain for the universe itself? The mortality of stars. By the mid-20th century, astrophysics had revealed that every star is bound by a clock. Its mass determines its fate. The massive blue giants, burning furiously, live for mere millions of years before collapsing in cataclysm. Medium-sized stars, like the Sun, endure for billions, ending as white dwarfs. The smallest red dwarfs, cool, dim, and ancient, will shine the longest. Lasting for trillions of years, the numbers themselves were staggering. Stars would live far longer than Earth, longer than galaxies in their current forms. Yet the conclusion was unavoidable. Every star, no matter how vast or humble, would eventually exhaust its fuel. There would come a time when fusion, the process that powers the cosmos, would cease. The scale of time to confront this reality was to confront time on an incomprehensible scale. Human history spans mere thousands of years. Even the age of Earth is only 4.5 billion. But the long night lies not millions, but trillions upon trillions of years ahead. The longest-lived red dwarfs will shine for up to 10 trillion years, a span 1,000 times the current age of the universe. Yet even that is a number with an ending. What lay beyond was not more starlight, but silence. The reign of entropy. This revelation intertwined with another unsettling principle, entropy. The second law of thermodynamics states that energy spreads, disorder grows, and usable energy declines. Stars are local triumphs against entropy, temporary engines of order and light, but their work cannot last forever. Once their fuel is gone, entropy prevails. Energy spreads too thinly to ignite new stars. The cosmos, on the grandest scale, tends toward equilibrium, a state of heat death, where no usable energy remains. The universe is not only aging, it is winding down. The death of illusions, the realization struck like a quiet thunder. The sky of stars, once seen as eternal, is revealed as temporary. The galaxies, vibrant with stellar nurseries, will fade. Even the black holes, once thought eternal, will evaporate through Hawking radiation. There will be no eternal structures, no everlasting light. This was a reversal of ancient belief, a collapse of comfort. The stars are not forever. The cosmos itself is fragile. The strange comfort of scale for some, the sheer immensity of the timeline softened the shock. 10 trillion years is vast beyond comprehension. Compared to human lifespans, even compared to the entire history of life. On Earth, it feels endless, but the comfort is deceptive. The scale may be immense, but the trajectory is certain. However long the stellar era lasts, it will end. The long night is not avoided by distance in time. It is guaranteed by the laws of physics, the contradiction of creation and death. This truth carries a haunting contradiction. The very processes that make stars mortal are the same that allow life to exist. Nuclear fusion cannot burn forever, but without it, there would be no warmth, no planets, no chemistry of life. Entropy ensures eventual silence, but it also powers the temporary triumphs, the blazing suns, the biospheres, the consciousness that now reflects upon them. The laws that create also destroy. The very reason we exist is inseparable from the reason we must fade. The fear behind the science, the scientific shock, then, is not only the numbers, the trillions of years, the inevitability of entropy. It is the recognition that the universe's story has an ending written into its beginning. Unlike myths that promised eternal cycles of renewal, physics reveals a one-way path. The cosmos began in fire, and it will end in silence. This is not merely theory. It is the consequence of equations tested in laboratories, of starlight analyzed through telescopes, of thermodynamic laws confirmed with every experiment. The fate of the stars is not speculation, it is certainty. The scale of human fragility yet here lies a deeper wound. Humanity exists in a fleeting moment, a thin sliver of time between the birth of the universe and its long night. Our entire history unfolds in the cosmic morning, while the stars still burn. The stars that guided travelers, inspired poets, and seeded life itself are temporary. They will vanish. The very stage of existence will be gone. The shock is not only cosmic, it is personal. For to know the fate of the stars is to know the fate of meaning itself. The question that remains: if the stars will die, if entropy will prevail, then what becomes of the universe afterward? Is the long night a final silence, or a transformation? Does the cosmos fade into darkness without return, or do hidden laws await to write another act? The scientific shock opens the door to this deeper mystery. The death of stars is not the end of questioning, but its beginning. The stars are mortal. The long night is certain, but what lies within that night remains unknown. The revelation that stars must die was only the beginning. To grasp the fate of the cosmos after the final embers fade, science turned its gaze toward stellar remnants, the mechanics of quantum decay, and the simulations of cosmic futures that reach far beyond the current age. What emerged was a portrait of a universe that does not end suddenly, but drifts into shadow. Each stage of its decline marked by the silent rule of physics. The white dwarfs, cooling embers when a star like the sun exhausts its nuclear fuel. It sheds its outer layers, leaving behind a dense core, a white dwarf, composed mostly of carbon and oxygen, supported by the pressure of electrons themselves. These stellar corpses shine faintly with residual heat. White dwarfs no longer fuse atoms, they only cool. Over billions, then trillions of years, they radiate their warmth into space, fading ever dimmer. Eventually, they will become black dwarfs, frozen, lightless husks, drifting in darkness. Though no black dwarf yet exists, the universe is too young. Their inevitability is written into physics. They are the ghosts of stars, the first actors in the slow play of the long night. Neutron stars, crushed matter more. Massive stars end more violently. When their fuel runs out, their cores collapse in a titanic implosion, compressing protons and electrons into neutrons. The result is a neutron star, a sphere barely 20 kilometers across, yet containing more mass than the Sun. Neutron stars are cosmic paradoxes, ultra-dense matter balanced precariously by quantum pressure, spinning with unimaginable speed, beaming radiation like celestial lighthouses. Yet even these remnants are mortal. Their magnetism weakens, their rotation slow. In the long night, they too will fade, cooling into dark. Inert spheres of nuclear matter, black holes, gravity's most massive stars collapse beyond neutron density, creating black holes. These are regions where gravity overwhelms all forces, curving space-time into a trap from which not even light can escape. For centuries, black holes were thought eternal, the indestructible end of matter. But Stephen Hawking's groundbreaking insight in the 1970s changed everything. Black holes are not perfectly black. Quantum effects at their event horizons cause them to emit faint radiation, slowly losing mass in the process, over unimaginable spans, years for a stellar mass black hole, and up to 10,100 years. For the supermassive giants at galactic centers, even black holes will evaporate. Their death is not violent, but a slow exhalation of particles, leaving behind only the faintest whispers of radiation. In the long night, black holes will glow weakly, then fade. Gravity's triumph is temporary. The role of quantum mechanics beyond stellar remnants lies an even stranger frontier: the fate of matter itself. Quantum field theory suggests that even seemingly stable particles may not last forever. Some grand unified theories predict that protons, the building blocks of atoms, can decay, transforming into lighter particles over 1,034 years or more. If true, then even the remnants of stars, white dwarfs, neutron stars, and black dwarfs will dissolve into radiation. The universe will not merely go dark. It will become thin, dissolving into elementary particles and fading energy. Though proton decay has not yet been observed, experiments such as Super Kamiokande continue to search. The silence of protons may be temporary. Their betrayal would mark the next stage of cosmic death. Simulating the futurist straphists have extended these insights into vast time, charting the eras of the universe. The stellar era now to approximately Y a years. Stars shine, burn out, and form remnants. The degenerate era approximately Y a to Y years, dominated by white dwarfs, neutron stars, and black dwarfs. Slowly cooling, the black hole era approximately YY2, 10,100 years. Black holes consume remnants, then evaporate. The dark era beyond 10,100 years. Only particles, radiation, and thin dust remain. Each stage grows longer, stretching time into incomprehensible scales. The age of stars, which feels eternal to us, is but the opening chapter. The long night extends far beyond. The faint glow in the darkness, though the night will be deep, it will not be absolute at once. In the degenerate era, white dwarfs and neutron stars will still radiate faint heat. Collisions of brown dwarfs. Failed stars, too small for fusion, may briefly ignite, producing dim flashes of starlight. Later, in the black hole era, the universe will not be entirely silent. Black holes, through Hawking radiation, will glow faintly, slowly losing their mass. But these lights are fragile, rare, and temporary. They are embers, not flames, sparks in a vast and growing void. The question of the unknown, the deeper science looked into this future. The more mysteries appeared. Does proton decay truly occur? If so, the long night ends not with black dwarfs, but with dissolution. Will dark matter, the invisible substance outweighing ordinary matter, remain forever, or decay into something stranger? Could vacuum, instability, hidden in the fabric of the Higgs field, rewrite physics itself in an instant, obliterating even the faintest remnant? The simulations are precise, but they rest on laws that may themselves be incomplete. The long night may hold surprises yet. The deepening of the mystery, the deeper the investigation goes, the clearer the paradox becomes. The same physics that explains stellar life cycles now points unavoidably toward a universe without stars. The remnants we observe today, cooling white dwarfs, spinning neutron stars, feeding black holes, are not anomalies, but precursors of a universal fate. Every observation of stellar death is a glimpse of the far future. Every remnant is a fragment of the night to come. The central image, the discovery phase, revealed stars as mortal. The scientific shock showed entropy's inevitable triumph, but deeper investigation paints the image of the long night in detail. a cosmos ruled by remnants, by silence, by the slow unraveling of matter itself. It is not a sudden catastrophe, but a fading, a long descent into shadow. The end of the universe is not fire, but quiet. Not an explosion, but a sigh. The deeper science projected into the universe's future, the darker and more unsettling the vision became. The death of stars and the slow cooling of their remnants were only preludes. Beyond them lies an era when the most powerful objects in the cosmos, black holes themselves, dominate, then vanish. And beyond even that, the universe faces questions so profound they stretch the limits of physics, the decay of matter, the acceleration of expansion, the stability of the vacuum itself. Each revelation escalates the mystery. The cosmos is not drifting into a simple silence, but unraveling into a state that may be stranger, more terrifying, and more final than imagination can fully bear. The age of black holes, when stars have long since burned out and white dwarfs cooled into invisible black dwarfs. The cosmos will enter the black hole era. Galaxies will still persist, but stripped of starlight. Gravity will continue its silent work, drawing stellar remnants inward, feeding black holes at their centers. Over quadrillions of years, encounters between wandering remnants will drive many into these dark abysses. Supermassive black holes, millions to billions of times the sun's mass, will preside over the silent galaxies. They will be the last beacons of gravitational power in a cosmos without stars. But even these titans are not eternal. Hawking's insight reveals that black holes emit faint radiation, losing energy slowly. The smallest black holes will evaporate first, then the larger ones, until even the supermassive giants fade into nothingness over timescales of 100 years. The last great structures of the universe will not collapse in fire, but dissolve in a whisper of radiation. The threat of proton decay, the unraveling, may go deeper still. If grand, unified theories are correct, then protons themselves, the foundation of atoms, are not perfectly stable. Over 1034 years or more, they may decay into lighter particles. If this is true, then every remnant, every black dwarf, every neutron star, every fragment of matter will eventually disintegrate. The long night will not only be dark, but matterlose. The very building blocks of the universe will betray themselves, leaving only radiation and ghostly particles adrift in an infinite void. Though experiments have not yet confirmed proton decay, the possibility hangs over physics like a prophecy, unresolved but haunting. The expansion without ending, another escalation, lies in the nature of space itself. In 1998, astronomers discovered that the universe's expansion is accelerating, driven by a mysterious force called dark energy. If this acceleration continues, galaxies will drift ever farther apart. Eventually, most galaxies will recede beyond the cosmic horizon, vanishing from view forever. Local groups of galaxies may remain bound, but across the vastness, isolation will reign. In the long night, even the faint companionship of distant galaxies will be gone. Each island of matter will be surrounded by an ocean of emptiness, expanding endlessly. The night will not only be dark, it will be lonely. The vacuum's fragility, and yet there is a possibility even more unsettling: the measured mass of the Higgs boson suggests that our universe may be in a false vacuum, a state, not the true ground of reality. If so, then one day, perhaps unprovoked, the vacuum could decay. A bubble of true vacuum could appear, expanding at the speed of light, rewriting the laws of physics as it spreads. The forces that shape atoms, stars, and life would be obliterated, replaced by new laws. This would end the long night, not in quiet, but in sudden annihilation. And it would arrive without warning, impossible to outrun. The universe, fragile from its first moment, would end not with entropy, but with collapse of the very fabric of its being. The escalating silence each of these revelations deepens the silence of the long night. First, stars die, then their remnants fade. Black holes preside, then vanish. Protons themselves may betray existence. Space expands, stretching matter apart into isolation, and perhaps the very vacuum beneath reality is unstable, awaiting collapse. The trajectory is not toward new creation, but toward dissolution. A universe that once blazed with light and structure appears destined to become thin, cold, and empty. The silence grows deeper with each layer of physics revealed. The mirror of human fear, the escalation, is not only scientific, it mirrors a deeper, more human fear that all things end, that permanence is illusion. The universe reflects this truth on the grandest possible scale. Stars die, black holes vanish. Even the laws of physics may fracture. To contemplate the long night is to confront mortality, not of individuals, not of civilizations, but of reality itself. The mystery that deepens end, yet the mystery resists closure. Will protons decay? Is dark energy constant, or will it shift into something stranger? Is the vacuum truly unstable? These questions remain unanswered. The deeper science looks, the less certain the future becomes. What seems inevitable is the darkness, but what lies within it? Silence, transformation, or something unimaginable remains veiled. The long night is more than a prediction. It is a question written into the structure of the universe, unanswered even by the deepest theories. The escalation summarized the death of stars was only the first revelation. The true escalation lies in the recognition that no structure, no matter, no law of physics may be permanent. The long night is not merely the absence of light, but the unraveling of all things, galaxies, particles, even the vacuum itself. The cosmos, it seems, carries within it the seeds not of eternity, but of dissolution. And yet, in this terrifying vision lies the deepest mystery of all. If everything ends, might ending itself be a gateway to something beyond? The vision of the long night is not a single story, but a branching tapestry of possibilities. Physics provides multiple paths forward, each drawn from the laws we know, each extended into speculation that brushes against the edge of imagination. None is certain. All are profound. Together they form a gallery of possible endings or transformations. For the universe after the last star fades, the heat, death. The universe in equilibrium, the most widely accepted fate, is the heat death, also called the Big Freeze. In this vision, entropy reaches its maximum. All usable energy is spent. Every process that could create structure or complexity comes to an end. Galaxies dissolve. Black holes evaporate. Matter itself decays, until only a thin fog of particles and radiation fills the cosmos. This is not dramatic fire, but perfect stillness, a universe in thermal equilibrium, where no event is more likely than any other, where time itself loses meaning because nothing changes. It is the most chilling vision because it is so quiet. The long night ends, not in violence, but in silence so complete it erases even the memory of motion. Proton decay, matter's betrayal. If protons are unstable, then the fate is even more severe. The very atoms that form stars, planets, and life would eventually crumble. Black dwarfs, neutron stars, and any surviving remnants would dissolve into lighter particles. Over 1034 years or longer, the universe would become a sea of radiation, bereft of structure. Matter itself would not survive the long night, though, unconfirmed, this possibility is embedded in some grand unified theories, which attempt to unite the forces of nature into a single framework. If these theories are correct, the betrayal of matter is inevitable. The evaporation of black holes. If protons endure, black holes will not. Hawking radiation ensures that they, too, fade away. The evaporation is unimaginably slow, but inevitable. In their final moments, black holes may flare briefly, releasing their last energy before dissolving. Afterward, nothing larger than subatomic particles would remain. The universe that began in blazing fire would end, in particles drifting endlessly. A cosmic haze, vacuum decay, sudden annihilation. Yet another possibility lies hidden in the Higgs field. Current measurements suggest that our universe may be in a false vacuum, a metastable state. If this is true, then one day, without warning, a bubble of true vacuum could appear, expanding at the speed of light. Within it, the laws of physics would be rewritten. Atoms, stars, and space itself would vanish. Unlike heat death, this fate would not take trillions of years. It would be sudden, total, and inescapable. The long night might end not in silence, but in a single, catastrophic instant. Cyclic universes, the promise of rebirth. Some theories suggest that the universe may not be heading for permanent silence. Instead, it may be part of a cycle, a cosmos that collapses and expands again. Eternally reborn. In big bounce models, expansion eventually halts, reverses, and collapses into a new singularity from which another universe emerges. Each cycle may shatter and reform symmetries differently, giving rise to new laws of physics, new stars, new possibilities. If so, the long night is not death, but gestation, the silence before a new dawn, the multiverse, endless variations. Other speculations extend further into the concept of the multiverse. If inflation is eternal, then countless bubble universes may exist, each born from quantum fluctuations, each with its own laws. In this vision, the death of our universe is not the death of reality. Beyond our horizon, countless other cosmoses blaze with stars, live through their own long nights, and give way to futures as strange as ours. The long night becomes not an ending, but one chapter in an infinite library of universes, quantum fluctuations, the resurrection of order. Even within heat death, there is a speculative possibility. Quantum mechanics suggests that fluctuations can occur in even the emptiest vacuum. Given infinite time, random fluctuations might assemble new particles, new structures, perhaps even entire universes. These possibilities, sometimes called Boltzmann brains or spontaneous universes, are controversial, but they reveal a haunting thought in an eternity of silence. Even randomness can give birth to order. In such a cosmos, the long night is not final. It is a stage upon which improbable new realities might emerge. The anthropic reflection, these speculations raise a sobering perspective. Perhaps our universe's fate is not unique. If many universes exist, each may follow its own trajectory, some collapsing, some freezing, some rebirthing. We observe this one because it permits observers. In this reflection lies an unsettling possibility. Our universe may simply be one in which the balance of forces allowed stars to shine, life to emerge, and consciousness to wander before the inevitable descent into silence. The common thread, though the theories differ, a common truth unites them. The long night is not avoidable, whether in trillions of years or in a sudden vacuum collapse. The era of stars will end, but whether silence is final or the prelude to something new remains unknown. The speculative paradox, the paradox of speculation, is this: the more possibilities we uncover, the less certain the future becomes. Heat death, proton decay, black hole evaporation, vacuum collapse, cyclic rebirth, multiverse branching, quantum fluctuation, each offers a vision. None can yet be proven. The mystery grows deeper with each theory. The long night after the last star is not only a prediction, it is a canvas for the deepest questions of physics, philosophy, and existence. To peer into the future of the cosmos, a future beyond stars, beyond galaxies, beyond matter itself, may seem impossible, and yet science has already built tools to explore this fate. They do not look forward in time in the way myth or prophecy once did. Instead, they examine the present with exquisite precision, using the laws of physics to extend vision across trillions of years. These instruments, from particle detectors buried beneath mountains to telescopes orbiting Earth, are humanity's eyes into the long night. Each experiment is a fragment of an answer, a step toward understanding what awaits when the last star has died. The oldest stars, measuring cosmic lifespans. Astronomers study the oldest stars in the Milky Way to test models of stellar lifespans. Ancient red dwarfs, faint and cool, reveal how slowly hydrogen fusion can proceed. These observations help refine predictions for how long stars can endure. And when the last generation will fade, white dwarfs provide another clue. By measuring their cooling rates, astrophysicists can project how they will one day become invisible black dwarfs. No black dwarfs yet exist, but the models are strengthened by the fading heat of the remnants already observed in these dying stars. The fate of the cosmos is written. Proton decay experiments, testing matter's endurance if matter itself can decay. Then the long night will not only be dark but matter. To test this, fast detectors have been constructed, such as Super Kamiokande in Japan, a chamber filled with 50,000 tons of pure water, buried deep underground to shield it from cosmic rays. Physicists watch for the faint flashes of light that would signal a proton's decay. None has yet been observed, but the silence only pushes the possible lifespan higher. Future experiments, like Dune in the United States, aim to extend this search. To observe proton decay would be to glimpse directly into the universe's farthest future, to witness the unraveling of matter itself. Black holes and gravitational waves. Black holes will dominate the universe long after stars are gone. To understand their fate, physicists study them today, using instruments like the Event Horizon Telescope, which captured the first image of a black hole's shadow, and LIGO Virgo, which detect gravitational waves from their collisions. These observations confirm Einstein's predictions and offer insights into how black holes consume matter, merge, and evolve. They also test the quantum theories behind Hawking radiation, the process that ensures black holes are not eternal, though we cannot yet detect Hawking radiation. Efforts to model and simulate it bring us closer to knowing how black holes will vanish in the far future. the cosmic microwave background, probing vacuum stability. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang. Missions like Planck have mapped it with exquisite precision, revealing clues about inflation and the universe's energy fields. Future observatories, like CMB's 4, will probe even deeper. These instruments may detect signatures of primordial gravitational waves, revealing phase transitions in the early universe. Such discoveries could clarify whether the Higgs field is stable or metastable, whether the vacuum itself might one day decay in this faint radiation. The question of the universe's ultimate stability is hidden. Dark energy surveys, measuring the expansion, the acceleration of cosmic expansion, is one of the greatest mysteries shaping the long night. If dark energy is constant, the universe will expand forever. If it evolves, the future may take a different course, perhaps even reversing. Surveys like Euclid, launched by the European Space Agency and NASA's upcoming Roman Space Telescope, are mapping galaxies and supernova across billions of light years. Their goal is to measure how dark energy behaves over time. The results will decide whether galaxies vanish forever into isolation or whether some unexpected fate awaits. Quantum experiments, testing the void, even the emptiness of space is not truly empty. Quantum mechanics predicts fluctuations in the vacuum, momentary appearances of particle-antiparticle pairs. In the laboratory, physicists are testing the quantum vacuum, probing its energy and stability. Experiments in particle colliders and quantum computing may reveal whether the vacuum is truly stable, or whether it hides the potential for sudden decay. In these fragile fluctuations may lie the universe's deepest secret, whether the long night is eternal, or whether it will be ended in an instant. The precision frontier. Not all tools are massive. Some are delicate, probing nature's symmetries at the smallest scales. Measurements of the muon's magnetic moment hint at deviations from the standard model of physics. Rare particle decays, tiny asymmetries, and subtle forces are tested with unprecedented precision. Each result carries implications for the far future. If new forces or particles exist, they may shape the long night in ways we do not yet imagine. The horizon of discovery, the search is not over. Proposed next-generation colliders could probe energies far beyond the Higgs, testing proton decay and vacuum stability. Space-based gravitational wave detectors like LISA may listen for signals from the earliest phase transitions. Deeper dark matter detectors may reveal particles that influence the fate of structure in the far universe. Each new instrument is a window, not only into the beginning of time, but into its end. The human dimension. It is striking to consider the scale of this endeavor. Humanity, existing for only a heartbeat of cosmic history, has already built machines that ask questions trillions of years beyond its own survival. The instruments we construct are not only tools of science, they are symbols of longing, our refusal to let the night fall without seeking to understand it. We will not see the last star die. We will not witness black holes evaporate or protons decay. But we can predict, calculate, and seek the laws that decide those fates. In doing so, we become participants in the story of the cosmos's end, even from within its briefest morning. The limits of science, and yet there are limits. Some questions may remain forever beyond reach. We may never know with certainty if the vacuum is stable, if protons decay, if other universes exist. The horizon of knowledge, like the cosmic horizon itself, may forever retreat as we chase it, But this does not diminish the search. To ask the question of the long night is to affirm the value of knowledge itself, to confront silence with inquiry, the tools as beacons in the end. These tools are more than machines. They are beacons lit against the coming dark. Colliders, telescopes, detectors, each is a spark of human curiosity, illuminating not only the past, but the unimaginable futures that await when the last star has gone. The journey into the fate of the universe has carried us from blazing galaxies to the silence of the farthest future. It began with stars, brilliant, innumerable, seemingly eternal. It ends with darkness, a cosmos emptied of starlight, drifting into silence. And yet, in contemplating this end, we uncover not despair, but a deeper reflection on existence itself. The fragile window of light, the universe, has not always known stars. For its first hundreds of millions of years, it was dark, filled only with hydrogen, helium, and the faint afterglow of the Big Bang. Then, gravity gathered matter into the first luminous spheres. The universe ignited, and the stellar era began. It is within this fleeting window between the darkness before stars and the darkness after that life has emerged. Consciousness has arisen precisely in the moment when the cosmos burns with light. We are children of this narrow dawn. The paradox of impermanence to know that stars are temporary is to recognize the fragility of all things. But impermanence is not emptiness. It is the condition of creation. Without entropy, without change, no structures would form, no stars would ignite, no lives would unfold. The same physics that ensures the universe's eventual silence also ensures that we exist at all. The paradox is haunting. Our mortality is shared by the stars, and it is through that mortality that existence itself becomes possible. The silence, as mirror the long night after the last star, can feel like an erasure, the undoing of everything. But perhaps it is also a mirror, reflecting our own longing for permanence. We seek stability in a cosmos that offers only change. We dream of eternity, but find ourselves in a universe built on imperfection and time. And yet, this recognition can deepen meaning. For if nothing lasts, then everything becomes precious. Each star, each life, each moment of awareness shines brighter against the certainty of silence. The possible beyond speculations of heat death, proton decay, black hole, evaporation, or vacuum collapse may describe endings, but endings may also be beginnings unseen. A cyclic cosmos, a multiverse, or quantum fluctuations may seed new realities beyond our own. Perhaps the long night is not final, but a transition, silence before another act in the play of existence. Perhaps creation and destruction are not opposites, but phases of the same rhythm, the same cosmic breath. Even if these speculations remain unprovable, they remind us that mystery endures. The night may hold not only darkness, but possibility, the human reflection for humanity. The lesson of the long night is not despair, but perspective. Our lives are brief, our civilizations younger still, but our questions reach across trillions of years. The very act of asking what comes after the last star affirms our place in the cosmos. We cannot change the universe's fate, but in knowing it, we transform it into meaning. We are the witnesses of impermanence, the storytellers of eternity, the final imagery picture, the universe now. Galaxies ablaze, stars scattered like jewels across the black. Picture it again, trillions of years hence, darkness, remnants, silence. The curtain falls, the stage empties, the cosmos sleeps, and yet, in this silence, one truth remains. The light that once was cannot be undone. The stars have burned, the galaxies have spun, life has gazed upward and wondered. That history, once lived, is eternal in its having been. The long night does not erase the brilliance. It is the backdrop against which that brilliance shines. The universe began in brilliance. It will end in silence. And between the two lies the fragile miracle of existence. To live in this brief window of starlight is to stand at the center of the only act in which life can appear, the luminous interlude between two infinities of dark. The long night after the last star is certain, but so too is this. The stars have burned, and we have seen them, and in that seeing, the universe has known itself.